Picture this: the universe keeps a ledger of all its matter, but every time scientists check the books, a staggering amount has simply vanished. Not dark matter, not some exotic particle, but the very stuff that makes up stars, planets, and even you. Baryonic matter, the building blocks of everything we see, is playing an interstellar game of hide and seek, and for decades, the brightest minds have been left scratching their heads. Where did it go? How does nearly half the universe's expected matter just disappear without a trace? This isn't science fiction. It's one of cosmology's greatest unsolved mysteries. Think of baryons like the flour in a cosmic recipe. We know exactly how much should be there based on the afterglow of the Big Bang and the way elements first formed. Yet when we tally up all the galaxies, gas, and dust we can observe, the numbers don't add up. It's as if someone took a giant eraser and wiped out a significant chunk of the universe's ingredients. The implications are staggering. If we're missing something this fundamental, what else don't we understand about how the cosmos works? But here's where the story gets thrilling. Clues are scattered across the universe, hidden in the faint glow of million-degree gas, the distorted whispers of ancient light, and the sudden bursts of radio waves from distant galaxies. Over the next 25 revelations, we're going to piece together this cosmic detective story, following the trail of breadcrumbs left by nature itself. Some answers will surprise you, others will challenge everything you thought you knew, and by the end you'll see the universe and its disappearing act in a whole new light. Ready to solve the mystery? Let's begin. Now, let's zoom in on the first major clue, the Cosmic Inventory Mismatch. Imagine baking a cake where you carefully measure every ingredient, only to find half the batter is gone when you pull it out of the oven. That's essentially what happened when scientists compared the universe's early recipe to what we see today. The cosmic microwave background, or CMB, is like a snapshot of the universe just 380,000 years after the Big Bang. It's the oldest light we can observe, and it tells us exactly how much baryonic matter existed back then. Combine that with Big Bang nucleosynthesis, the process that cooked up the first hydrogen and helium, and you get a precise prediction. About 5% of the universe's total energy should be baryons. But here's the shocker. When we count up all the stars, galaxies, and visible gas in the modern universe, we're coming up short, way short. Nearly half the baryons are missing. This discrepancy wasn't just a minor rounding error. It was a glaring red flag, forcing scientists to confront a baffling question. If the matter didn't vanish, where did it go? The hunt for answers had officially begun. Now, let's turn our attention to a fascinating possibility, the Warm-Hot Intergalactic Medium, or WHIM. Picture the universe not as a collection of isolated galaxies, but as a vast, intricate spiderweb with strands of superheated gas stretching between them. This cosmic web is where scientists believe a significant chunk of those missing baryons might be hiding. The WHIM is made up of gas so hot, reaching temperatures of millions of degrees, that it glows faintly in X-rays, but it's also incredibly thin. Imagine trying to spot a single light bulb in a foggy city from miles away. That's the challenge astronomers face when searching for this diffuse material. Its low density means it doesn't emit much light, making it nearly invisible to most telescopes. But here's where simulations like Illustris come in. These powerful computer models recreate the universe's structure, showing how baryons could be spread out along these faint filaments. The simulations suggest that up to 50% of the missing matter might be lurking in this elusive web. The catch: detecting it requires cutting-edge technology and a bit of cosmic luck. So while the WHIM remains a leading suspect in the case of the missing baryons, proving its guilt is still one of astronomy's greatest challenges. Now, here's where things get even more intriguing. Astronomers have a clever trick up their sleeves to spot the WHIM ghostly presence. They use distant quasars, some of the brightest objects in the universe, as cosmic flashlights. Picture a quasar as a lighthouse billions of light years away, its beam piercing through the vast stretches of space. As that light travels, it passes through the WHIM faint filaments, and here's the key. The gas leaves behind tiny fingerprints in the form of absorption lines. These absorption lines are like barcodes etched into the quasar's light. Specific elements in the WHIM, like highly ionized oxygen known as O7 and O8, absorb certain wavelengths of light, leaving dark notches in the quasar's spectrum. It's how scientists can say, aha, there's a wisp of million-degree gas right there. But there's a catch. These lines are incredibly faint, like trying to spot a whisper in a roaring concert. That's why only the most sensitive telescopes like Hubble can catch them. Landmark projects like the Hubble Spectroscopic Legacy Archive have been game-changers, compiling decades of quasar observations to hunt for these elusive signals. Even then, it's painstaking work like sifting through static to find a faint radio signal. But every detection adds another piece to the puzzle, slowly revealing where the universe has stashed its missing baryons. Now, let's turn our attention to another fascinating piece of the puzzle, the Sunyaev-Zeldovich effect. Imagine the cosmic microwave background, that ancient glow from the Big Bang, as a vast ocean of light filling the universe. When this light passes through galaxy clusters, something remarkable happens. The hot gas in these clusters, packed with electrons, scatters the CMB photons, leaving behind a subtle but detectable distortion. It's like seeing the shadow of a cloud passing in front of the sun, except here, the cloud is a massive cluster of galaxies, and the sun is the afterglow of creation itself. This effect, named after the scientists who first predicted it, has become a powerful tool for hunting missing baryons. Surveys like Planck and the Atacama Cosmology telescope have scanned the sky, mapping these distortions to pinpoint where hot gas lurks in galaxy clusters. What they found was eye-opening. These clusters hold a significant chunk of the universe's baryons, roughly 15%. That's a big step toward closing the gap in our cosmic inventory. But here's the twist. While these surveys confirmed where some baryons were hiding, they also revealed something unexpected. The bulk of the missing matter wasn't in these dense clusters after all. Instead, the hunt had to shift to the emptier, low-density regions of space, the voids and filaments where the WHIM might be hiding. This clue didn't just add to the map, it redirected the entire search, showing astronomers where to look next. The Sunyaev-Zeldovich effect didn't solve the mystery, but it sure narrowed down the suspects. Just when astronomers thought they'd exhausted every tool in their cosmic detective kit, along came fast radio bursts, those mysterious millisecond flashes of radio waves from deep space. At first glance, these fleeting signals might seem like just another cosmic oddity, but here's the twist. They're actually some of the universe's most precise scales. When an FRB races across the cosmos, its journey isn't smooth. The burst gets stretched out as it plows through clouds of electrons in its path, a phenomenon called dispersion. The more electrons it encounters, the more its signal slows and spreads. Think of it like a beam of light passing through a prism, except instead of colors, we're measuring the invisible stuff between galaxies. By analyzing this dispersion, astronomers can tally up the electrons along the FRB's route. And since electrons are glued to protons in baryonic matter, this indirectly reveals where the missing baryons are hiding. Projects like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and Australia's Square Kilometre Array Pathfinder, ASCAP, have turned this idea into a game-changing technique. CHIME's sprawling radio telescopes, for instance, catch dozens of FRBs every month, each one a snapshot of the electron density across vast cosmic distances. Meanwhile, ASCAP pinpoint accuracy lets astronomers trace bursts back to their home galaxies, adding crucial context to the measurements. What makes FRBs so powerful is their ability to probe the warm-hot intergalactic medium, that elusive WHIM we've been chasing. Unlike other methods that struggle to detect this diffuse gas, FRBs can essentially weigh it by measuring how much their signals are dispersed. Early results are already hinting that a substantial fraction of missing baryons might be lurking in these faint filamentary structures. So while fast radio bursts might be brief, their impact on solving the missing baryon problem that could last for decades. Now, let's shift our gaze to the turbulent forces within galaxies themselves, because sometimes the universe doesn't just hide its secrets in the voids between galaxies, but flings them outward in spectacular cosmic gusts. Enter galactic winds, the powerful outflows driven by the most violent events in a galaxy's life, supernova explosions and the voracious appetites of supermassive black holes. When a massive star reaches the end of its life and explodes as a supernova, it doesn't go quietly. The blast unleashes enough energy to hurl surrounding gas, packed with baryons far beyond the galaxy's disk. Meanwhile, active black holes at galactic centers add their own fury, heating up gas and launching it into space at speeds that can reach millions of miles per hour. Together, these processes act like cosmic bellows, ejecting a staggering 30 to 50% of a galaxy's baryons into the surrounding circumgalactic medium, or CGM. Simulations have been pivotal in uncovering just how much material these winds carry. Models like Illustris and Fire show intricate webs of outflowing gas, with baryons often traveling hundreds of thousands of light-years before settling into the CGM's diffuse halo. But here's the catch: observing these winds in action is notoriously tricky. Why? Because the same regions where winds blow are also where galaxies accrete fresh gas from their surroundings. Telling apart the ejected material from the incoming fuel is like trying to track individual leaves in a swirling autumn gust, possible, but requiring incredibly precise tools. This is where cutting-edge telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope come into play. By analyzing the chemical fingerprints and velocities of gas in the CGM, astronomers hope to untangle the messy history of galactic winds. Early clues suggest that without these outflows, galaxies would look very different, perhaps even brimming with far more visible baryons than we see today. So while galactic winds might scatter baryons into the shadows, they're also a vital piece of the puzzle, reminding us that sometimes the key to finding what's missing lies in understanding what's been violently pushed away. Now let's zoom in on the vast, invisible ocean that surrounds galaxies, the circumgalactic medium, or CGM. Think of it as a sprawling reservoir of gas, dust, and crucially, baryons, stretching tens of thousands of light-years beyond a galaxy's visible edges. This isn't just empty space, it's a dynamic region where material cycles in and out, acting as both a storage unit and a recycling center for the galaxy's baryonic matter. One of the most revealing glimpses into the CGM's secrets comes from the Cosmic Origins Spectrograph Halos Survey, or COS halos. By studying the light from distant quasars as it passes through the CGMs of foreground galaxies, astronomers detected something telling: strong signatures of ionized oxygen. This isn't just random gas, it's evidence of baryons lingering in these extended halos, often at temperatures too hot to form stars but too cool to glow brightly in X-rays. The survey suggested that the CGM could hold as much as half of a galaxy's expected baryons, a staggering amount that had previously flown under the radar. But here's where the debate heats up. Are these baryons truly missing, or are we just seeing them differently? Some argue that the CGM's baryons have been hiding in plain sight, their faint signals overlooked by earlier telescopes. Others counter that even with advanced instruments, we're only catching a fraction of the CGM's total content, leaving a gap in our cosmic accounting. The challenge lies in the CGM's complexity. Its gas exists in multiple phases, from scorching hot to relatively cool, and each requires different techniques to detect. This ambiguity makes the CGM a fascinating frontier in the missing baryon puzzle. It forces us to ask, if so much baryonic matter is right there enveloping galaxies, What does that mean for the rest of the missing fraction? Could better tools like next-generation spectrographs finally bring these hidden reservoirs into sharp focus? The answers might not just solve a cosmic mystery, they could rewrite how we see galaxies and their evolution. Now, let's turn our attention to the smallest players in the cosmic arena, dwarf galaxies. These tiny, faint systems might seem insignificant, but they hold big clues about the missing baryon problem. Unlike their larger counterparts, dwarf galaxies appear to be shockingly short on baryons, often containing just a fraction of what models predict. So why does this happen? The answer lies in a cosmic tug-of-war between gravity and stellar forces. Dwarf galaxies have one major disadvantage: their weak gravity. Imagine trying to hold onto a handful of sand in a strong wind. That's essentially what these galaxies face. When stars form, they don't just sit quietly. They explode as supernova, unleashing powerful winds that can blow gas right out of the galaxy. With such feeble gravity, dwarf galaxies struggle to cling to their baryons, losing them to the vast intergalactic void. This explains why many dwarfs end up gas-poor and baryon-deficient, leaving astronomers scratching their heads over the discrepancy. But nature loves exceptions, and that's where galaxies like Leo P come in. This tiny dwarf is a rebel packed with gas and forming new stars despite its small size. How does it defy the trend? The answer might lie in its quiet life. Unlike more active dwarfs, Leo P hasn't experienced intense stellar explosions, meaning its gas hasn't been blown away. Other gas-rich dwarfs, like those found in isolated regions, also challenge the idea that all small galaxies must lose their baryons. These outliers force us to rethink the rules. Could environment or star-forming history play a bigger role than we thought? The mystery of dwarf galaxies isn't just about missing baryons, it's about understanding the delicate balance between creation and destruction in the cosmos. If even the smallest galaxies can defy expectations, what does that mean for the bigger picture? As we piece together these clues, we're not just solving a puzzle, we're uncovering the hidden rules that shape the universe. Shifting our gaze closer to home, let's examine what we know about baryons in our cosmic neighborhood, the low redshift universe. This is where astronomers roll up their sleeves and take a meticulous inventory, combing through galaxies, gas clouds, and even the spaces between them to account for every last baryon. But here's the catch: no matter how carefully we tally, a significant chunk remains missing. The most comprehensive effort to solve this cosmic accounting problem came in 2018, when a team led by astronomer Michael Scholl compiled data from across the electromagnetic spectrum: X-rays, ultraviolet, optical, even radio waves. Their goal: to pin down how much ordinary matter exists within about half the observable universe's radius. The results were eye-opening. They found roughly 60% of the baryons predicted by Big Bang nucleosynthesis. That's a solid majority, but it still leaves a staggering 40% unaccounted for. So where did the rest go? The Scholl study pointed to two likely hiding spots. First, the warm-hot intergalactic medium, that elusive million-degree gas threading through cosmic filaments. Second, the circumgalactic medium, the extended halos of gas surrounding galaxies. Both are devilishly hard to detect because they're either too diffuse or too faint to stand out against the cosmic background. This census isn't just a head count, it's a roadmap. By revealing where baryons aren't, it forces us to refine our search strategies. Maybe we need more sensitive X-ray telescopes to spot faint WHIM emissions. Or perhaps future radio arrays will catch the whispers of hidden gas in galaxy halos. One thing's clear: the low redshift universe still holds secrets, and each uncovered baryon brings us closer to solving the mystery. Now let's turn the clock back even further. If today's universe is missing baryons, what about the ancient cosmos? That's where our next clue takes us, into the high redshift frontier where the story takes a surprising twist. Here's the next section of the script, seamlessly continuing from the previous segment while introducing the new clue with a smooth transition. Now, let's rewind the cosmic clock. If today's universe is missing a hefty chunk of baryons, what happens when we peer back to its younger days? This brings us to our 10th clue, the high redshift baryon abundance, where the story takes a fascinating turn. Observations of the early universe reveal something startling. Nearly all the expected baryons seem to be present. Studies of galaxies and gas clouds at high redshifts, when the cosmos was just a fraction of its current age, show baryon counts that align almost perfectly with predictions from Big Bang nucleosynthesis. It's as if the universe started with a full tank of gas, only to spring a leak over billions of years. So what changed? There are two compelling possibilities. First, maybe baryons didn't vanish at all. They just became harder to spot as the universe evolved. In the early cosmos, baryons were densely packed in galaxies and bright gas clouds, glowing fiercely in ultraviolet and X-ray light. But as the universe expanded, these structures thinned out, scattering baryons into dim, diffuse phases like the WHIM or the CGM, where they're now hiding in plain sight. The second possibility is even more intriguing. Perhaps baryons did disappear, not by vanishing into thin air, but by transforming into forms we can't easily detect. Could supermassive black holes or dark energy have played a role in sequestering them? Or might there be exotic physics at work, altering how baryons interact over cosmic time? This clue forces us to confront a critical question. Is the missing baryon problem a detective story about flawed tools, or is it a cosmic heist with baryons slipping away into the shadows? The answer could reshape our understanding of how the universe grows and what it's made of. Up next, we'll explore how dark matter's invisible grip might be holding onto these elusive baryons, pulling them into hidden corners of the cosmos. Now, let's turn our attention to the invisible scaffolding of the cosmos' dark matter halos, and how their gravitational pull might be the key to unlocking the mystery of the missing baryons. Dark matter doesn't just shape the universe's large-scale structure, it also acts like a cosmic trap for baryons. These invisible halos, which surround galaxies and galaxy clusters, exert a powerful gravitational force pulling baryons into their grasp. Think of it like a spider's web where dark matter forms the sticky threads and baryons are the particles caught in its grip. One of the most fascinating discoveries in this area is the concept of the splashback radius. This is the boundary where baryons, after being pulled inward by a halo's gravity, reach their farthest point before falling back in. It's like tossing a ball into the air. It rises, slows, and then reverses direction. At this outer edge, baryons pile up, creating a dense ring of gas that's incredibly difficult to detect because it's so spread out and faint. Cutting-edge simulations like the Eagle project have shown that these halos could be major reservoirs of baryons. The data suggests that a significant fraction of the universe's missing baryons might be lurking in the form of hot, diffuse gas within these dark matter halos. The challenge: this gas doesn't emit much light, making it nearly invisible to our telescopes. So, if dark matter halos are hiding baryons, why haven't we found them all yet? Part of the problem is temperature. The gas in these regions is often so hot that it radiates weakly in X-rays, blending into the background noise of the universe. Another issue is distance. These halos extend far beyond the visible edges of galaxies, making them easy to overlook in surveys. This clue reshapes our search, suggesting that the missing baryons might not be lost at all, just hiding in the vast, dark outskirts of galaxies, held there by the relentless pull of dark matter. Next, we'll zoom in closer to home, examining the cold, dense clouds of gas that might be another piece of this cosmic puzzle. Now, let's shift our gaze to something a little closer to home: cold, mysterious clouds drifting through the halos of galaxies. These aren't your average cosmic gas formations. Clocking in at around 10,000 degrees Kelvin, They're far cooler than the million-degree plasma we've been discussing, yet they might hold vital clues to the missing baryon puzzle. Astronomers first spotted these chilly clouds through their ultraviolet absorption lines. When distant quasars shine their light through these gas patches, certain wavelengths get absorbed, leaving behind a fingerprint in the spectrum. It's like holding a prism up to a light bulb and seeing which colors go missing, except here, the missing colors tell us about the gas's temperature, density, and even its motion. But here's the debate. Are these clouds fresh fuel falling into galaxies, or are they leftovers ejected by galactic winds? Some researchers argue they're accreting material, gas that's slowly raining down to feed star formation. Others think they're the opposite, blown outward by supernova or black hole activity, destined to linger in the halo or even escape entirely. The truth might be a mix of both, with some clouds falling in while others are cast away. A perfect example is right in our cosmic backyard, the Smith cloud. This massive hydrogen cloud, hurtling toward the Milky Way at nearly 200 miles per second, is either a returning splash of galactic fountain material or an incoming dwarf galaxy's shredded remains. Either way, it's packed with enough gas to form millions of stars, proving that these cold clouds aren't just minor details, they're major players in the baryon budget. So, do these cool clouds account for the missing baryons? Probably not all of them, but they're a crucial piece of the puzzle, showing that the circumgalactic medium isn't just a scorching void. It's a dynamic, layered ecosystem of gas in all its forms. Next, we'll dive into another cosmic detective tool, the intricate web of hydrogen absorption known as the Lyman alpha forest. Now, let's step into the cosmic jungle, a tangled web of hydrogen clues known as the Lyman alpha forest. Picture this: when light from a distant quasar travels across the universe, it doesn't arrive untouched. Instead, it passes through countless clouds of hydrogen gas, each one absorbing a tiny slice of that light at a specific wavelength. The result, a spectrum that looks like a forest of absorption lines, each one a fingerprint left by hydrogen atoms along the quasar's path. This forest isn't just random noise, it's a detailed map of the universe's large-scale structure. The closer a hydrogen cloud is to us, the more its absorption line shifts toward the red end of the spectrum due to the expansion of the universe. By studying how these lines evolve with redshift, astronomers can trace how baryons are distributed across cosmic time. At higher redshifts, when the universe was younger and denser, the forest is thick with lines, revealing a time when baryons were packed tightly together. As we look closer to the present day, the lines thin out, showing how the universe's expansion has stretched and diluted these gas clouds. But here's the catch: the Lyman alpha forest has its blind spots. While it's brilliant at mapping cooler, neutral hydrogen, it struggles to detect the hottest phases of the warm-hot intergalactic medium, the very places where a significant chunk of missing baryons might be hiding. That's because at temperatures above 100,000 degrees, hydrogen atoms get ionized, stripping away the electrons that create those telltale absorption lines. So while the forest gives us a wealth of data, it's only part of the story. Still, this method has been a game changer. By combining Lyman alpha data with other tools, like X-ray observations of ionized metals or the Sunyaev-Zeldovich effect, scientists can cross-check where baryons might be lurking. It's like piecing together a puzzle where each clue fills in a different part of the picture. Up next, we'll explore how another cosmic mystery, the so-called missing metals, might actually help us track down those elusive baryons. Now, here's a twist in the cosmic detective story. What if the key to finding missing baryons isn't just about hydrogen, but also about the universe's heavier elements? Let's talk about the missing metals problem. Metals in astronomy aren't just what you'd find in a toolbox. They're any element heavier than helium, forged in the hearts of stars and scattered across the cosmos by supernova and galactic winds. And here's the thing, just like baryons, a significant fraction of these metals seem to have vanished without a trace. But this might actually be a lucky break for astronomers. Unlike hydrogen, which can become invisible when ionized, metals leave behind more stubborn fingerprints. Elements like oxygen, carbon, and neon absorb or emit light at specific wavelengths, even when they're part of that million-degree gas in the warm-hot intergalactic medium. That means metals could act as cosmic breadcrumbs, leading us straight to the missing baryons. For example, highly ionized oxygen like O7 or O8 creates sharp absorption lines in X-ray and ultraviolet spectra, even in environments where hydrogen has been stripped of its electrons. This idea has already sparked some exciting breakthroughs. Surveys using telescopes like Chandra and XMM Newton have spotted metal signatures in the WHIM, hinting at vast reservoirs of ionized gas that were previously invisible. And because metals tend to cluster where baryons are densest, they could help pinpoint the exact locations where missing matter is hiding. It's like switching from a blurry black and white photo to a high-resolution color image. Suddenly, details pop out that were impossible to see before. Of course, there are challenges. Metal lines are faint, and teasing them out from the cosmic background requires incredibly sensitive instruments. But upcoming missions like Athena and Lynx are designed to do exactly that. By combining metal detections with other clues like the Lyman alpha forest or fast radio bursts, scientists are inching closer to solving both the missing metals and missing baryons puzzles at once. So while hydrogen might be the star of the show, don't underestimate the supporting role of metals. They could be the breakthrough we've been waiting for. Next up, we'll dive into another powerful tool in this cosmic hunt: baryon acoustic oscillations, the faint echoes of the early universe that could help us weigh the cosmos. Now, let's turn our attention to a cosmic echo from the dawn of time: baryon acoustic oscillations. Picture the early universe as a vast, seething soup of particles where gravity and pressure battled for dominance. When the universe was just a few 100,000 years old, sound waves rippled through this primordial plasma, creating regions where matter was slightly denser or sparser. These ripples froze in place when the cosmos cooled enough for atoms to form, leaving behind a faint but detectable pattern, like fossilized waves in the fabric of space. Today, we can still see this pattern imprinted in the way galaxies are distributed across the sky. By measuring the average distance between galaxy clusters, about 500 million light-years, scientists can trace those ancient sound waves and use them to estimate the total amount of baryonic matter in the universe. It's like measuring the spacing of tree rings to figure out how old a forest is, but on a cosmic scale. This is where projects like the Dark Energy Spectroscopic Instrument, or DAISY, and the Baryon Oscillation Spectroscopic Survey, BOSS, come into play. These ambitious surveys map millions of galaxies with pinpoint precision, using baryon acoustic oscillations as a cosmic ruler. The results: they've helped narrow down the universe's baryon density to within a few % of predictions from the cosmic microwave background. That means most of the missing baryons aren't truly missing. They're just hiding in forms we're still learning to detect, like the warm-hot intergalactic medium or the circumgalactic gas around galaxies. What makes baryon acoustic oscillations so powerful is their simplicity. Unlike other methods that rely on interpreting faint signals or complex models, BAO provides a straightforward, geometric way to weigh the cosmos. And as future surveys map even more galaxies, this cosmic ruler will become even sharper, helping us close the gap between theory and observation. Up next, we'll explore another major reservoir of baryons, the scorching hot gas trapped in galaxy clusters, and why it's only part of the puzzle. Now, let's step into the blazing heart of galaxy clusters, where temperatures soar to millions of degrees and a hidden ocean of baryons swirls in plain sight. This is the intracluster medium, the superheated gas that fills the spaces between galaxies in these cosmic metropolises. While stars and galaxies grab the spotlight, the real heavyweight here is this invisible, scorching plasma, which alone accounts for roughly 15% of all the baryonic matter in the universe. X-ray telescopes like Chandra have been game changers in studying this extreme environment. Unlike optical telescopes that see starlight, Chandra detects high-energy X-rays emitted by the intracluster medium as electrons whip around at nearly the speed of light. These observations reveal intricate structures, vast rivers of gas, shock waves from colliding clusters, and even the fingerprints of supermassive black holes stirring the cosmic pot. One of Chandra's most stunning discoveries was the bullet cluster, where the intracluster medium lagged behind the galaxies during a collision, proving that most of a cluster's mass is invisible dark matter. But here's the catch: while the intracluster medium is packed with baryons, it's still just a fraction of what the universe should contain. Even after tallying up all this hot gas along with the stars and cold gas in galaxies, we're still short by about 40%. That tells us the intracluster medium is a major piece of the puzzle, but not the full answer. So where does that leave us? The hunt continues, with next-generation X-ray telescopes like Lynx and Athena poised to probe even fainter, hotter gas in the cosmic web. Up next, we'll explore how galaxies themselves might be recycling baryons in a process that could help explain where the rest have gone. Now, let's zoom in closer to home, right into our own Milky Way, where a cosmic recycling program has been quietly at work for billions of years. Picture this: gas isn't just sitting still in galaxies. It's constantly moving like water in a fountain, cycling between the star-filled disk and the surrounding halo. This is the galactic fountain model, and it might hold clues to where some of those missing baryons have been hiding. Here's how it works. When massive stars explode as supernova, or when supermassive black holes at galactic centers unleash powerful jets, they blast gas outward at incredible speeds. This gas shoots up into the halo, where it can cool and condense, eventually raining back down onto the disk to fuel new generations of stars. It's a breathtaking cycle, one that's been observed in our own backyard. The Fermi bubbles, towering structures of hot gas stretching 25,000 light-years above and below the Milky Way center, are a smoking gun. These colossal outflows, likely powered by past activity of our galaxy's central black hole, show just how far fountain material can travel. But here's the twist. What if some of this gas doesn't make it back? Simulations suggest that under certain conditions, fountain material could be ejected entirely, escaping a galaxy's gravitational grip and joining the vast, hard-to-detect reservoirs of the circumgalactic medium. Could these fountains be sneaking baryons into places our telescopes struggle to see? It's a tantalizing possibility, one that turns galaxies from static islands of stars into dynamic players in the missing baryon mystery. As we piece together this galactic recycling story, the next clue takes us even deeper into the invisible forces shaping where baryons end up. Now, let's unravel a fascinating twist in this cosmic detective story, one where the missing baryons might actually be pulling the strings behind the scenes. Imagine a galaxy struggling to form new stars, not because it lacks potential, but because something invisible is siphoning away its fuel. This is the missing baryon feedback loop, a process where the very baryons we can't detect could be dictating how galaxies grow. Here's how it plays out. When stars explode or black holes flare up, they don't just eject gas, they create powerful feedback that can heat up or even expel surrounding material. In some galaxies, especially smaller ones with weaker gravity, this feedback might be so intense that it kicks baryons out for good, cutting off the supply of star-forming gas. The result: galaxies that should be bustling with new stars instead appear strangely quiet, their growth stunted by these unseen losses. Recent simulations paint a vivid picture. In models like those from the Eagle project, feedback doesn't just redistribute baryons, it can permanently eject them into the vast intergalactic void. This might explain why some galaxies, particularly dwarfs, seem to have far fewer baryons than expected. Their gas reservoirs aren't just hiding, they've been blown away, escaping into regions so diffuse that our telescopes can't spot them. But here's the kicker. This feedback loop isn't just a one-way street. By regulating how much gas stays in a galaxy, these missing baryons could be shaping the entire cosmic ecosystem, determining which galaxies thrive and which fade into obscurity. It's a humbling thought that the matter we've been searching for might be the very force controlling the universe's grand narrative. As we ponder this invisible hand guiding galaxy evolution, our next clue takes us even further into the shadows, where faint glows and elusive signals might finally reveal the baryons we've been missing. Now let's turn our attention to something closer to home, our very own Milky Way. If you've ever looked up at the night sky, you've seen stars, planets, and maybe even the faint band of our galaxy. But there's something else out there, something far harder to spot. A soft glow of X-rays and ultraviolet light emanating from the Milky Way's halo. This diffuse emission might just be another piece of the missing baryon puzzle. Here's the mystery. When astronomers point their telescopes toward the halo, the vast, sparse region surrounding our galaxy, they detect this faint but persistent glow. The question is, what's causing it? One possibility is that it's coming from hot gas, heated to millions of degrees, floating in the halo. If that gas is part of the Milky Way's own reservoir, it could mean we're seeing local material, not the elusive missing baryons. But there's another tantalizing idea. What if this glow is actually the signature of the missing baryons themselves, spread so thin across the cosmic web that they're nearly invisible except for this faint emission? This is where missions like eROSITA come in. This advanced X-ray telescope, scanning the sky with unprecedented sensitivity, is designed to map this diffuse glow in incredible detail. By analyzing the energy and distribution of these X-rays, scientists hope to determine whether they're tracing ordinary galactic gas or something far more significant, the hidden baryons we've been searching for. Early results suggest a mix of both, with some emission tied to known structures and other parts still unexplained. The debate isn't settled yet. Some argue that the glow is too patchy to account for all the missing baryons, while others believe we're only seeing the tip of the iceberg. Either way, this faint light serves as a reminder that sometimes the answers we seek are hiding in plain sight, or in this case, in the dim glow of our own galactic backyard. And as we continue our search, our next clue takes us even deeper into the unknown, where high-energy particles might be masking the very baryons we're trying to find. Now, let's venture into the high-energy realm of cosmic rays, particles racing through space at nearly the speed of light. These aren't just random streaks of energy. They might hold the key to understanding where some of those missing baryons are hiding. Here's how it works. Cosmic rays, often flung into space by supernova or active black holes, don't just travel harmlessly through the universe. When they collide with gas in the circumgalactic medium, the vast, sparse halo around galaxies, they can ionize that gas, stripping electrons from atoms. This process leaves the gas in a strange, nearly invisible state. It's still there, but it doesn't emit much light, making it incredibly hard to detect with traditional telescopes. Think of it like fog on a dark night. You know it's there because the air feels thick, but you can't see it clearly unless a light shines through it. Similarly, cosmic rays might be turning baryons into this cosmic fog, hiding them in plain sight. Some studies suggest that the pressure from these high-energy particles could even prevent gas from cooling and falling back into galaxies, trapping baryons in these hard-to-spot regions for billions of years. This idea isn't just speculation. Observations of galaxies with strong cosmic ray activity often show less gas than expected in their immediate surroundings, as if something is pushing it away or masking it. Simulations back this up, showing how cosmic rays can create vast, diffuse reservoirs of ionized gas in galactic halos, reservoirs that could account for a chunk of the missing baryon budget. Of course, there's still debate. Not all cosmic rays behave the same way, and their exact impact on gas retention is still being studied. But one thing's clear: if we want to solve the missing baryon puzzle, we can't ignore these high-speed particles. They might be the invisible hand shaping where and how baryons hide. And as we peel back another layer of this cosmic mystery, our next clue takes us into the realm of magnetic fields, where invisible forces could be corralling baryons in ways we're only beginning to understand. Now, let's turn our attention to another invisible force shaping the cosmic landscape: magnetic fields. These aren't just the stuff of refrigerator magnets or compass needles. They're powerful, unseen threads weaving through the universe, and they might be playing a crucial role in hiding baryons from our view. Here's the fascinating part. Magnetic fields can act like cosmic cages, trapping and confining baryons in ways that make them incredibly difficult to detect. Imagine a spiderweb so fine that it's nearly invisible, yet strong enough to hold droplets of water in place. Similarly, magnetic fields could be pinning baryons into diffuse, hard-to-spot structures, especially in the vast halos around galaxies. This isn't just theoretical observations of so-called dark galaxies like Dragonfly 44 suggest this might already be happening. Dragonfly 44 is a bizarre cosmic oddity. It has the mass of a galaxy like the Milky Way, but almost none of the stars. Instead, it's packed with dark matter and possibly baryons locked away by intense magnetic fields. If magnetic fields are strong enough, they could prevent gas from collapsing to form stars, leaving it in a ghostly, dispersed state. That would explain why we see so little light from these objects, even though they might be brimming with baryons. The idea gains traction when you look at simulations. Models show that magnetic fields can stabilize gas clouds, keeping them from clumping together or emitting detectable radiation. In some cases, these fields might even funnel baryons into vast, magnetized filaments, part of the cosmic web where they remain hidden in plain sight. Of course, there are still puzzles to solve. Measuring magnetic fields across intergalactic space is no easy task, and their exact influence on baryon distribution is still being debated. But one thing's certain: if we're going to find those missing baryons, we can't overlook the role of these invisible forces. They might be the silent architects of the universe's biggest hiding spots. And as we unravel this magnetic mystery, our next clue takes us even deeper into the cosmic timeline, exploring how baryons have evolved over billions of years and why they might have been easier to spot in the universe's youth. Now, let's journey back in time to uncover how the universe's baryon budget has shifted over billions of years. Picture the cosmos in its younger days, around what astronomers call cosmic noon, a bustling era roughly 10 billion years ago when galaxies were forming stars at breakneck speeds. Back then, baryons weren't playing hide and seek. They were front and center, lighting up the universe in ways we can still trace today. Thanks to powerful telescopes like ALMA, which peers into the distant universe with incredible precision, we've caught glimpses of these gas-rich early galaxies. ALMA observations reveal something striking. These ancient galaxies were swimming in baryons, with vast reservoirs of gas fueling their star-forming frenzy. Unlike today, where baryons seem to have vanished into the cosmic shadows, the universe's youth was a time of abundance, with baryons far easier to spot. So what changed as the universe expanded and galaxies evolved? Baryons didn't just disappear, they transformed. Some got locked up in stars or black holes, while others were blasted out into intergalactic space by violent supernova or active galactic nuclei. Over time, these ejected baryons became more diffuse, blending into the warm-hot intergalactic medium or hiding in the faint outskirts of galaxy halos. The result, a universe where baryons are still here, just harder to see. This timeline isn't just a curiosity, it's a crucial clue. If baryons were more visible in the past, it suggests the missing ones today aren't truly gone. They've simply shifted into forms or places that challenge our detection methods. By studying cosmic noon, we're not just looking backward, we're piecing together a roadmap of where baryons might be hiding now. And as we connect these dots across time, Our next clue will spotlight the cutting-edge tools poised to bring the universe's hidden matter into sharper focus. Now, let's turn our attention to a game-changing tool in the hunt for missing baryons, one that listens to the faint whispers of hydrogen atoms across the cosmos. Imagine tuning a radio to catch signals from the universe's earliest days, but instead of music, you're picking up the signature of hydrogen, the most abundant element in existence. This is the promise of 21-centimeter cosmology, a technique that could revolutionize how we map baryons in both their neutral and ionized forms. At the heart of this method is the 21-centimeter line, a faint radio signal emitted by hydrogen atoms as their electrons flip their spin states. When this light travels through space, it gets stretched or compressed by the gas it passes through, leaving behind a fingerprint of where baryons are hiding. The beauty of this approach, it doesn't just spot dense clouds of hydrogen, it can also detect the wispy, ionized gas that makes up the cooler parts of the warm-hot intergalactic medium, the very places where missing baryons might be lurking. Enter the Square Kilometre Array, or SCAR, a next-generation radio telescope set to be the most sensitive instrument of its kind. With thousands of antennas spread across 2 continents, SKA will scan the sky with unprecedented precision, stitching together a 3-dimensional map of cosmic hydrogen. Think of it as turning on a flashlight in a dark room. Suddenly, the faintest structures, like the tendrils of gas connecting galaxies, come into view. But why is this such a big deal? Until now, we've relied heavily on X-rays and ultraviolet light to hunt for baryons, which limits us to spotting only the hottest gas. The 21-centimeter line, though, opens a window to the cooler, more elusive phases of the WHIM, filling in gaps that other methods can't touch. It's like finally being able to see the entire puzzle, not just the brightest pieces. And here's the kicker: this isn't just about finding baryons. By tracing hydrogen's distribution, we'll also uncover how galaxies grow, how cosmic webs form, and even how the first stars ignited. It's a tool that doesn't just solve one mystery, it rewrites our understanding of the universe's structure. As we stand on the brink of this new era in astronomy, one thing's clear: the missing baryons won't stay hidden forever. With 21-centimeter cosmology leading the charge, we're closer than ever to closing the cosmic ledger once and for all. Now, let's take a step back and consider the bigger picture. If we've learned anything from this cosmic detective story, it's that no single tool can crack the case of the missing baryons alone. That's where the multi-messenger approach comes in, a strategy that combines the strengths of different wavelengths to paint a complete portrait of where baryons are hiding. Think of it like assembling a jigsaw puzzle where each piece comes from a different box. X-rays reveal the scorching hot gas, ultraviolet light catches the warm filaments, optical telescopes track the cooler clouds, and radio waves map the faintest hydrogen signals. Together, they cover the full spectrum of where baryons could be lurking. Leading this charge are next-generation observatories like Athena and Lynx, set to launch in the coming years. Athena, an X-ray telescope with a resolution 10 times sharper than current instruments, will peer into the heart of galaxy clusters and the diffuse gas between them, hunting for baryons in the hottest phases of the warm-hot intergalactic medium. Meanwhile, Lynx will complement this by zooming in on fainter X-ray signals, almost like switching from standard definition to ultra-high definition. These missions won't just spot baryons, they'll study their movements, temperatures, and even their chemical makeup, giving us clues about how they've been scattered across the cosmos. But the real power of the multi-messenger approach lies in synergy. By cross-referencing data from X-ray, UV, optical, and radio surveys, astronomers can spot connections that would be invisible to any one telescope. For example, a faint X-ray glow might trace the same filament of gas that's subtly dimming a quasar's ultraviolet light, or a radio signal from hydrogen could overlap with a patch of ionized gas detected by an optical telescope. It's these overlapping clues that will finally help us account for every last baryon. And here's the exciting part. This isn't just about filling in a cosmic spreadsheet. The multi-messenger approach could reveal how baryons cycle in and out of galaxies, how they fuel star formation, or even how they're ejected by supermassive black holes. It's a way to see the universe's plumbing system in action, from the largest scales down to the finest details. So as we gear up for this new era of astronomy, one thing's certain: the missing baryons won't stand a chance against the combined might of our telescopes. Whether they are hiding in scorching intergalactic threads or faint radio whispers, we're bringing the full arsenal of science to bear, and the universe's last great inventory problem might finally be solved. Now, let's turn our attention to the digital universe, where cutting-edge simulations are rewriting the rules of the cosmic hunt. The simulation revolution is giving us a powerful new tool to track down missing baryons, not with telescopes but with supercomputers. Projects like Illustris the Next Generation, or Illustris TNG for short, are creating virtual cosmos so detailed they can follow individual baryons across billions of years. These aren't just video games for scientists, they're laboratories where we can test theories about how baryons move, hide, and interact on scales no telescope could ever see. What makes these next-gen simulations so groundbreaking? They don't just mimic the universe, they challenge it. By comparing virtual skies with real observations, astronomers can spot mismatches that reveal where our detection methods fall short. For instance, if simulations predict a thick web of warm gas between galaxies, but our telescopes only catch faint traces of it, that gap tells us we're missing something. Maybe the gas is cooler, denser, or more spread out than we thought. It's like having a cheat sheet for the cosmos, showing us exactly where to look next. But here's the catch: simulations are only as good as the physics we program into them. One major hurdle: feedback. When stars explode or black holes flare up, they blast energy into their surroundings, pushing baryons into hard-to-detect corners of space. Current models struggle to capture these chaotic processes accurately, which means simulations might still be underestimating how far baryons can travel. That's why the next wave of virtual universes will focus on refining these feedback mechanisms, blending real-world data with ever more precise algorithms. The ultimate goal: a perfect digital twin of our universe, where every simulated baryon matches one in the real cosmos. We're not there yet, but with each upgrade: faster processors, sharper codes, better physics, we close another gap in the mystery. So while telescopes scan the skies, simulations light up the path forward, showing us not just where baryons are hiding, but why they've been so hard to find. And that might be the revolution that finally solves the case. Now, let's take a step back and consider something we don't often talk about in astronomy: the human mind. Even in the quest for missing baryons, our own biases can play tricks on us. Scientists call it the streetlight effect, where we tend to search only where it's easiest to look, like a person searching for lost keys under a lamppost simply because the light is better there. For decades, astronomers focused on the brightest, most obvious places: galaxies, clusters, and dense gas clouds, because that's where our telescopes worked best. But what if the missing baryons were never in those places to begin with? Some of the biggest breakthroughs in this mystery came when researchers dared to question the assumptions holding the field back. Take Dr. Jessica Work, an astrophysicist who challenged the idea that most baryons must be locked inside galaxies. Her work on the circumgalactic medium revealed vast reservoirs of gas right on the outskirts of galaxies, material everyone had overlooked because it was too faint and diffuse. Then there's Dr. Sebastiano Cantalupo, who pioneered new ways to detect the faint glow of intergalactic gas by using quasars as cosmic flashlights. These scientists didn't just rely on better instruments, they rewired how we think about the problem. The lesson here: sometimes the biggest obstacle isn't technical, it's in our own heads. We assume baryons should behave a certain way or exist in certain places because that's what our models and intuition tell us. But the universe doesn't care about our biases. The next clue in solving this cosmic puzzle might not come from a bigger telescope or faster supercomputer, but from a scientist willing to ask, what if we've been looking in the wrong places all along? And that's how the human factor, our creativity, our stubbornness, and even our mistakes could finally shine a light on the missing baryons. Now, let's take a step beyond the science and into the realm of philosophy. What if the missing baryons aren't just a detection problem, but a challenge to one of cosmology's foundational ideas, the cosmological principle? This principle assumes the universe is uniform on large scales, meaning matter should be spread evenly if you zoom out far enough. But what if it's not? Some theorists argue that the missing baryons might be hiding in plain sight, just unevenly distributed in ways we haven't mapped yet. Imagine a sponge. From a distance, it looks smooth, but up close, you see pockets of dense material and empty gaps. Could the universe's baryons be clustered in similar, hard-to-see structures, defying our expectations of uniformity? This wouldn't require new physics, just a tweak to how we model matter distribution. Others push back, pointing out that even if baryons are patchy, the sheer scale of the discrepancy suggests something deeper. If the universe were truly lumpy on large scales, it would upend everything from galaxy formation to dark matter theories. Yet, intriguingly, simulations like Illustris TNG show that baryons do clump in unexpected ways, especially in the cosmic web's faint tendrils. Maybe the real puzzle isn't where the baryons are, but why we're so attached to the idea of cosmic smoothness in the first place. So, is the cosmological principle at risk? Not necessarily, but the missing baryons force us to question whether we've overstated the universe's uniformity. Whether the answer lies in better maps or revised theories, one thing's clear: this mystery isn't just about matter. It's about how we perceive the cosmos itself, and that brings us to the final piece of the puzzle, tying all these clues together in our conclusion. Now, as we bring this cosmic detective story to a close, let's take a moment to reflect on the journey we've taken through these 25 clues. Each one, from the mismatched cosmic inventory to the philosophical questions about the universe's uniformity, has chipped away at the mystery of the missing baryons. While we haven't found all the answers yet, every clue has tightened the noose around this puzzle, ruling out dead ends and pointing us toward promising leads. Think of it like assembling a vast jigsaw puzzle where some pieces are still hidden. We've placed enough to see the outline, the warm-hot intergalactic medium, the roll of galactic winds, the whispers of fast radio bursts, but the full picture isn't complete. And that's the beauty of science. The gaps invite curiosity, pushing us to build better telescopes, refine simulations, and question old assumptions. So what's next? The hunt continues. Maybe the breakthrough will come from a future observatory like the Square Kilometre Array, or perhaps a sharp-eyed viewer like you will spot a pattern everyone else missed. After all, some of history's biggest discoveries started with someone asking, what if we've been looking at this all wrong? If this mystery has taught us anything, it's that the universe loves to surprise us. The missing baryons aren't just a scientific problem, they're a reminder that there's always more to learn, and that the next great revelation could be just around the corner. So stay curious, keep questioning, and who knows, you might be the one to finally solve the case. If you enjoyed this deep dive into cosmic detective work, don't forget to hit that like button and subscribe for more mysteries of the universe. Ring the notification bell so you never miss an update, and let us know in the comments which clue you think holds the key to cracking the baryon problem. Until next time, keep looking up.